today's lecture we continue our discussion on seasonal models. In the previous lecture we demonstrated a basic model considering seasonality. So, we looked at this data, and this data would represent the demand over 3 years, and each year is divided into 4 quarters. In the previous model we computed a seasonality index. For example, a seasonality index for the first quarter data of year 1 would be 53 divided by 157. The seasonality index for this number, which represents second quarter of year 1, would be 22 by 157 and so on, and we computed a seasonality matrix, and then we averaged the seasonality indices for every quarter. We also tried to forecast the next year's total demand by using the regression or the method of least square fit, and then we said that we could multiply the forecasted value with each of these indices to get the forecast for the 4 seasons for the next year. Now what we will see is, can we use exponential smoothing in some form to try and get a model which can in principle forecast better in the sense that more recent data will have more weightage. For example, when we used the method of least square to fit a line here, we gave equal weightage to all these points. Now the question is, can we use exponential smoothing and try and build another model to do this? Now that model is called the Winter's model, and the Winter's model has the following equations. So we use these equations for the Winter's model. At present these equations may look a little complicated, but it is easy to explain these 3 equations. Now A represents the level, or which is the base data, B represents the trend or the slope, and C represents the seasonality. Now there are 3 things in a seasonal model: a level, a trend and a seasonality. For example, to explain with this data, the level values are like 157, 173, 189. It actually exhibits both level and trend. One could think of 157 as a level, and then there is an increasing trend. So, there is a slope which takes it to 173 and then to 189 and so on. There is a seasonality. For example, the seasonality index associated with this is 53 divided by 157. So, now if we see that the level for a period t plus 1 has two parts exactly as in the exponential smoothing equation. Alpha is an smoothing constant. So, alpha times dt by ct, dt plus 1 by ct plus 1 minus alpha times at plus bt. Now, if we are in period t and at that time the level value is at, then the level value for the next period will be the earlier level plus slope. So, you have an at plus bt which kind of represents the at plus 1. Similarly, if there is a demand dt plus 1 in that period and there is an associated seasonality of t plus 1, so demand by seasonality would also give the level value at that period. Therefore, the actual level value of t plus 1 is a weighted average of this term and this term, where this is multiplied by alpha and this is multiplied by 1 minus alpha. So, if you are in period t and then we want to find out the level for period t plus 1, one can use this particular formula to get the level at period t plus 1. Now, similarly, slope at that period also has two components. Now, always the difference between two levels represents a slope. So, at plus 1 minus at is one measure of slope, and the slope at period t, which is bt, is another measure of slope. So, the slope at or for period t plus 1 is a weighted sum of two slopes. So, beta times at plus 1 minus at, which is again equivalent of a slope, and 1 minus beta times bt, where beta again is an exponential smoothing constant. Similarly, seasonality, you can see the subscript is t plus p plus 1, which essentially comes because if I am somewhere here, then I am in, this is, if this is called C1, C2, C3, C4, C5, C6, C7. So, if we are at 2 and the number of periods is 4, t plus p plus 1 is C7 is what we are computing, which is essentially computed from this as well as this. So, you will have dt plus 1 by at plus 1 demand, the demand by the total, the level which represents the total demand. This is a measure of a seasonality index. This is also the measure of seasonality index from the previous one. So, once again it is a weighted sum of two seasonality measures, where gamma is the exponential smoothing constant. Now, after we compute all these, we try and get the actual forecasted value, which is given by this equation. So, what we will do now is we will try and show some computations and explain how we do the calculations for the Winter's model. So, let us take the same example and do that. So, in order to do this, we also need to do some initialization. So, we will assume C1 to be equal to 0.34, which actually is 53 divided by 157. C2 is 0.14, C3 is 0.24 and C4 is 0.29. So, let us initialize these three values. Now, we also need to initialize A1, where A1 is the level at this period. So, A1 is initialized to 53 divided by 0.34, which is 156. There is a small rounding off error which is acceptable. 0.34 was obtained on the division of 53 divided by 157, so it is rounded off there. So, the rounded value gives us a 156 as the level value. So, we now know the level value here, which is A1. Now, we have to find out the level value for A2, the corresponding slope B2, and so on. So, we also use alpha equal to 0.2, beta equal to 0.3 and gamma equal to 0.25 as the smoothing constants. And we also need to use a value of B1, which is taken as 4, which is roughly the slope here, because 157, 173, the difference is 16 over 4 periods gives us a slope of 4. Once again 173, 189 gives us a slope of 4. So, we now have initialized all the values so that we can do these computations. So, let me show those computations again. So, A2, which is level for period 2, is 0.2 into 156 plus 0.8 into 156 plus 4, which is 159.43. Now, how do we get those numbers? AT plus 1 level for period 2 is alpha times dt plus 1 by Ct plus 1, alpha is 0.2 here. Now, dt plus 1 by Ct plus 1 is 156 that we have, plus 0.8 1 minus alpha into AT plus BT, which is A1 plus B1 160. So, the level moves up from 157 or 156 to 159.43 for the next period A2. Now, B2 is obtained from 0.3 into 159.43 minus 156 plus 0.7 into 4, which is 3.829. Now, this comes from this equation beta times A2 minus A1 159.43, which we just now calculated, minus A1, which is 156, 1 minus beta is 0.7, BT is B1, which is the earlier slope, which is 4. So, you get 3.829. Then we compute C6 is equal to, now essentially we are trying to look at seasonality for somewhere here using these seasonal values. So, C6 will be 0.25 into 22 divided by 159.43 plus 0.75 into 0.14. Now, these things come from gamma into dt plus 1 by AT plus 1, gamma is 0.25, dt plus 1 is 22, AT plus 1 we just calculated as 159.43. So, this is a measure of seasonality of this quarter, which is represented by C2, C6, C10. So, 22 divided by 159.43 is a measure of seasonality, plus 0.75 1 minus gamma into 0.14, which is the initialized value for C2. So, when we do this, C2 C6 becomes 0.1395. Now, from this we can initialize F3 forecast for period 3 is 159.43 into or plus 3.829 into 0.24, which is 39.18. Now, let us go back to F3 this is our F3, this is the actual period, D3 is known. So, the forecast for this is 139.18. That comes from the level at the end of 2 is 159.43. So, level plus slope would take it to 159.43 plus 3.829, which is here, and that is multiplied by the seasonality, which is 39.18. So, now we have shown one full round of calculations. Now, once this is known, we can continue the calculations by now starting to compute A3. So, A3 will now become alpha times D4 by C4 plus 1 minus alpha times, I am sorry, we compute A3. So, A3 is equal to alpha times D3 by C3 plus 1 minus alpha times A2 plus B2. So, now we know all the values. D3 can be got from here, which is 37, C3 is 0.24, alpha is known, 1 minus alpha therefore is known, A2 and B2 are calculated, are available there. So, we can calculate this A3. Similarly, we can calculate B3 as beta times A3 minus A2, A2 is known, A3 has been just calculated, 1 minus beta times B2, B2 is known from the previous one. So, we can calculate this one. Similarly, we can calculate C7 because gamma is known, D7 by A, this is 7. So, D3 by A3 is known plus 1 minus gamma, C3 is also known. So, we can calculate C7, from which we can calculate F4. So, we can continue with the Winter's model, and finally, we have a value F13 forecast for period 13 is 67.29 with the updated values. Seasonality values are also calculated accordingly and kept updated. So, finally, the forecast for period 13 is 67.29. So, if we want to forecast the value here from using Winter's model, we would get 67.29 here, and then we use this model to continue to compute this and so on. Now, what are the advantages of the Winter's model? One is we have used exponential smoothing. The very idea that we consider all the data points, we give more importance to or higher weightage to the more recent data points and so on. Now, all the three important things like level, slope and seasonality index are updated using a simple exponential model, where in some sense two things are captured, the value at period t and then the value at period t plus 1. So, they are captured in this, each has a two components connected by the weights, and the alpha, beta and gamma are the smoothing constants. And then we have a relationship that the forecast is level plus trend multiplied by seasonality. Now, this also answers a very interesting question that we posed in the previous lecture. Now, if we have a data like this, now can we simply take 53, 58, 62 and forecast the next value? Can we take 22, 25, 27 and forecast the next value? The answer to this is no from a forecasting point of view. The reason being the assumption that even though there is an increasing trend here, and the increase in trend is visible when we actually take the demand, total demand for the year, it becomes visible when we do that. If we see here, we see an increasing trend, but we do not actually see an increase in this direction, because the values are very different and they are multiplied by the corresponding seasonality index. By using the Winter's model, what we are trying to say here is that in some sense the 16 increase here is actually spread as 4 in each season, and that is the reason we also got something like 67.29, which is 62 plus some 4 plus something, that plus came because of the increased weights to more recent data. So, to that extent Winter's model is able to capture, is able to put into each period the fact that there is an increase and that increase is captured by deseasonalizing it. Second advantage perhaps is, if we were given the demand here, let us say if the actual demand here turned out to be 67 and then we want to make a forecast here, we could directly use these formulae and get the forecast here. Whereas if we had de-linked them and said I am going to do this and then something here without doing any of these, we are not capturing the effect of these data points on a subsequent forecast. So, Winter's method also helps us in trying to do the forecast with data which is not fully complete with respect to a year. You could have only 2 or 3 pieces of data and then you could do the fourth and then you could proceed. So, with this we have kind of seen forecasting models, essentially time series forecasting models for level data, which I called as a constant model, then for level plus trend and then level plus trend plus seasonality. So, we have essentially covered 3 aspects of it, which is level, trend and seasonality. Now, there are other things which also need to be covered in forecasting models. It is also customary to do what are called cyclic models or cyclicity, and usually cyclic models have a larger time period than the models that we have seen here, and cyclic models are usually represented using sinusoidal curves. So, we will have models of the form y is equal to a cos 2 pi t plus b sin 2 pi t, where t is the period and a and b are the constants that we try and find out. Once again we can use methods of least square to try and get the values of a and b which are for the cyclic models. The next thing that we will see right now is what are called causal models. In the causal models we try and fit something of the form y is equal to a plus bx, where y is the variable that we are actually trying to forecast. Now, it depends on another variable x, which is the independent variable, where y is the dependent variable that we are trying to forecast. The normal example given is, for the grain output would depend on the amount of rainfall. So, x is the independent variable which is your rainfall, for which we have the data, y is the dependent variable and then we want to forecast y for a given value of x. So, if we have, for example, 6 periods of data for the grain production and we will require 7 periods of data for the rainfall. So, for example, if we want to fit y equal to a plus bx, if we want to do y7, which is the forecast for period 7 for the variable y, or we can call it f7, which is the forecast for period 7, then that will be a plus 7. Now, we need a plus b into x7, where x7 is the data for the independent variable for period 7. Unlike in time series the forecast for period 7, the data we would use only up to period 6. In a causal model we also require data for the independent variable for period 7. Methodology wise, the fitting a plus bx and a plus bt are one and the same, except that x will replace t in the causal model. So, methodology wise it is the same. You can once again take y minus a minus bx the whole square, which represents the error sum of squares. Error sum of squares, we call it E square, is equal to sigma y minus a minus bx the whole square. Now one should also note that actually though we are trying to, while this is the model, we assume that the given data has a small noise or randomness which we call as epsilon, and then that creates a small error. Therefore y minus a minus bx is actually not 0 but some value. Otherwise if we start looking at y equal to a plus bx here, and when I write y minus a minus bx, then one would think that it is 0. It is actually not. There is a small error component whose square we actually try to minimize. Now we can partially differentiate with respect to a and b, which are the unknowns, to try and get the two equations, which is sigma y is equal to Na plus b sigma x, and sigma xy is equal to a sigma x plus b sigma x square. Now with these two equations we can try and solve for a and b. Now the solution is very similar to the time series, therefore I am not taking a numerical example to explain the same solution. Once again you will have columns for x, x square, x, y, x square and xy, and then we can solve for this. The how to solve this has been covered in an earlier lecture in this course. The only difference, as I said, is having obtained a and b, now if we have data for 6 periods for x and y, we could use data for 6 periods of x and y, and finally we will get something like y equal to a plus bx. Now for the 7th period, if we know the value of x7, if we know the value of the independent variable, then we will be able to substitute, because using these two we can get a and b. So we can substitute to get the value of y, which will be the forecast for the 7th period or a subsequent period. So this is how we address causal models. Now what is always possible to build causal models of different types, it need not be a plus bx. For example, we can build causal models of the form a plus bx1 plus cx2, or we can build a plus bx plus cx square, or we can build y equal to a x power b and so on. Now when we build y equal to a plus bx1 plus cx2, it means there are two independent variables which influence the behavior of the dependent variable y. So the methodology will now shift to minimizing sigma y minus a minus bx1 minus cx2 the whole square. So there are 3 unknowns a, b and c. So partially differentiate with respect to all the 3 of them to get 3 equations here instead of 2, and then we can solve those 3 simultaneous equations to get a, b and c. And for the period to which we want to forecast, we need the values of x1 and x2. We can substitute and try and get the actual value. If we fit a model like this, there is only one independent variable, but then there is a quadratic term here. So we will try and minimize y minus a minus bx minus cx square. Once again there are 3 things that we have to calculate, a, b and c. We will partially differentiate to get 3 equations. So we will get a third equation which will say sigma x square y is equal to a sigma x square plus b sigma x cubed. So there will be another term also, there will be a third term also. So you can partially differentiate it to get 3 equations involving 3 terms a, b and c, so that we can fit a quadratic and do it. If we fit a causal model of the type y equal to a x power b, then what we need to do is to take logarithm on both sides to get log y is equal to log a plus b log x. So this will become log y is equal to log a plus b log x. Now log y will be replaced by a variable y, this will be by another constant a plus log x will become another small variable x. So, now we fit small y is equal to capital A plus b small x. Now, this model is very similar to this model. So, we need to now instead of log a we will actually end up getting this a, and then from this a we need to go back to get this small a, because this is representative of log a. So, at some point these things become a little bit of substitution in mathematics, but the basic methodology is to try and fit something of the form a plus bx or a plus bx plus cx square or a plus bx1 plus cx2, and then try and minimize the error sum of squares and get the line of best fit, assuming linear, and if it is quadratic, the quadratic curve of the best fit. So, in almost all the causal models, the underlying methodology is to try and convert it to linear or quadratic as the case may be, and try and determine the line of best fit and then proceed. And as I said, the error sum of squares thing is very similar to what we have seen in the basic time series forecasting model. Now, we come to the last part of the forecasting, which is to try and find out the goodness of a forecast. Now, how good is the forecast is the question that we have to ask. The reason being, depending on our assumption, we actually have more than one model that we can use to forecast. Like if our assumption is that the data represents a constant model or the data represents only level, then we have seen several models. We have seen simple average, we have seen moving averages, we have seen exponential smoothing, all these if we have only level. If we had L plus T, that is level plus trend, we have seen two models. One is linear regression, line of best fit, and then we saw Holt's model. And if we have L plus T plus S, which means seasonality is also included, we saw a basic model and we saw Winter's model. So, depending on our assumption that the data represents only level or L plus T or L plus T plus S, we could use more than one model to try and get the forecast. So, how do we compare solutions of various models under the same assumption? If we believe that it represents only level, then we could use any one of the three or even a weighted moving average and so on. So, we could test with 4 or 5 models and then finally we have to choose one. Similarly, if the assumption is L plus T, then we could use both these models or other models that are available in the literature and then choose one, the forecast from one of these and so on. How do we do that? Now, that is called measuring the goodness of a forecast. Now, let me take a simple example to explain the goodness of the forecast. Now, let us explain it using a very simple example. So, let us take some data which is 30, 32, 33 and 35. Let us say this is the, or let us assume we take data which is 30, 32, 31, 30. Now, we can assume that this represents only level, because at the moment we do not see a visible trend here. So, let us say we take only level data, and let us say we are going to use the total comes to 123 is the total. So, simple average is 30.75 is the simple average. Now, there are several measures that we can define for the goodness of the forecast. So, we are going to do one is called mean absolute deviation, mean squared deviation, mean percentage deviation, and so on. So, let me show the calculation for some of these. Now, let us assume we are using simple average, and therefore, the forecast for all the 4 periods is 30.75 and forecast for a 5th period is also 30.75. So, mean absolute deviation in this case is, let us call it MAD, which is mean absolute deviation. Mean absolute deviation would be sum of this. So, 30 minus 30.75 plus 32 minus 30.75 plus 31 minus 30.75 plus 30 minus 30.75. Now, please note that we are finding out the absolute value and not the actual. So, this is 0.75 plus 1.25 plus 0.25 plus 0.75, which is 1.5 plus 1.5 is 3. For example, we did not do 30 minus 30.75 plus 32 minus 30.75 and so on. If we had done that, the value will be 0 because it is a simple average. So, we take the mean absolute deviation. Now, mean squared deviation is 30 minus 30.75 square plus 32 minus 30.75 square plus 31 minus square plus 30 minus square. So, coming back to this is not mean because this is the total absolute deviation, which is 3. So, mean absolute deviation will be 1 by n number of point wise. So, 3 by 4 will give us a 0.75 as mean absolute deviation. Now, mean square deviation will be, this is 0.75 square, which is 0.5625. This is 1.25 square, so 1.5625. This is again 0.31 minus 30.75 is 0.25, so 0.625 plus 0.5625. So, this would roughly be 0.56 is 1.12. So, 2.68, 2.74. So, this is roughly totals to about 2.75. That is the mean squared deviation. So, mean squared deviation will be this divided by 4. Now, mean percentage deviation can be, now the demand is 30, the forecast is 30.75. So, the deviation is 0.75. In fact, we could even qualify this as mean absolute percentage deviation. So, 0.75 is the absolute thing here. So, that divided by the forecast which is 0.75 divided by 30.75 into 100 plus 1.25 divided by 30.75 into 100 and so on. Now, the only difference here is these two will be related because the denominator is the forecast, which is 30.75, which is common. So, we can even do mean absolute percentage deviation with respect to demand and not with respect to forecast, so that these values can change now. So, these denominators will become by 30 by 32 plus 2 more terms and so on. So, one can define several terms like these, which basically represent the goodness of a forecast. Now, this value mean absolute deviation is 3, that 3 is total absolute deviation as I said, and mean absolute deviation is 3 by 4, mean squared deviation is 2.75 by 4 and so on. Now, if instead of simple average, if we had used a 2 period moving average, which means the forecast would have become 30.5 instead of 30.75, then we can calculate the mean absolute deviation. Now, for 30.5 forecast, mean absolute deviation will become 0.5 plus 1.5, 2, 2.5 plus 0.5, which happens to be 3 again. So, 0.5 plus 1.5 is 2, 2.5 plus 0.5 is 3. Now, mean squared deviation will become, for 30.5 it will become 0.25, mean squared deviation will become 0.5 square is 0.25, 1.5 square is 2.25, 31, so another 0.25 plus 30, another 0.25, say this will be about 3. So, this is 2.75 divided by 4, say this is 3 divided by 4, say. Therefore, this will show a smaller value of mean squared deviation than this forecast. This way, if we use more than one model here, we can choose one out of these goodness measures as the measure that we are going to use, and say for the sake of discussion we have chosen mean squared deviation. Now, we can evaluate the mean squared deviation for the forecast obtained by each of these, and then find out that model which has given us the least value of mean squared deviation. The example is, if we had used simple average, the mean squared deviation is about 2.75 by 4. If we had used a 2 period moving average, then the forecast is 30.5 and the mean squared deviation is 3. Therefore, we could say that if we had used mean squared deviation as the criterion to measure the goodness of a forecast, then the simple average is a better forecast than the moving average. But then one has to be a little guarded when we consistently choose mean squared deviation as the measure of goodness. If we look at it very carefully, statistically simple average is always the measure that will minimize the error sum of squares or mean squared deviation. The very definition of simple average comes from there. Therefore, if we take the simple average, it will always be better than any other forecasting method if we are using mean squared deviation as the criteria. So, usually mean squared deviation is not taken as the measure for measuring the goodness of a forecast. Normally, mean absolute deviation is taken as a measure for the goodness of a forecast, simply because mean squared deviation is kind of little bit biased towards the arithmetic mean. But another way of overcoming that is also this. Here what we did was we took all the arithmetic mean and then we said 30.75. We could have done something else. If we have only this data, the arithmetic mean is 30. If we have this data, the arithmetic mean is 31. If we have this data, the arithmetic mean is 31, and if we have all 4 data, arithmetic mean is 30.75. Now we can find the error sum of squares as 30 minus 30 square, 32 minus 31 square, 31 minus 31 square, 30 minus 30.75 square. If we start doing that, then our basic idea that simple average will always be the best when we use this measure need not happen. So there are several issues like this that we can look at, but the very basic idea is to look at one of the measures and use it consistently. Often the suggested measure is mean absolute deviation. Now use that measure, and then if you have forecast using more than one model, evaluate it based on this measure and choose that one which gives the minimum value. Then we can get into another question. For example, if we have a data which is like this, if we have a data which is like 30, 34, 36, 39, so clearly this data shows trend. So we could use this or this. For example, if we had 30, 32, 31, 30, at the moment we can say that it does not show trend, but one could say that let me try and fit y equal to a plus bt. B is going to be small if it does not show any trend, or B is going to be 0 if it does not show any trend. Can I do that? The answer is not. In principle, we have to check what are the assumptions, and after the assumptions we try and get the model. We do not want to fit a model and depending on the result of the model go back and correct our assumption, oh well this may exhibit trend. So that is not usually the practice. The other question is, if we have a set of data, now can I apply a model from here, can I apply a model from here and then choose the better one based on the goodness? The answer is actually no, the reason being the model that we choose should come after the assumptions that we make regarding the behavior of the data. So it is not a good idea to try and see whether moving average is better or whether linear regression is better after testing both the models and trying to find out the goodness. That is usually not practiced. What is actually good is to try and make the assumption that based on the assumption this exhibits level, therefore I am going to use one of these. This exhibits level plus trend, therefore I am going to use one of these, and so on. So with this we actually come to the end of the forecasting part of this course or this lecture series. So we kind of started the forecasting topic by saying that there is a need to forecast. There is a need to forecast because manufacturing organizations need to know how much they have to produce in the subsequent periods or in the subsequent months. So forecast is defined as the estimate of the future demand, and then we also said that the forecast can depend on only time, which led us to time series models. It can also depend on some other independent variables which led us to causal models. Within the time series we saw level, level plus trend plus seasonality, and we saw some causal models, and we also saw how to measure the goodness of a forecast. The next question that comes is, well, after the forecasting what do we do? Forecast has given us the estimate of the demand for a future period. Now what is the next step that we have to do in order to use this data that has come from forecast? Now that comes from what is called an aggregate production planning. We will now see the basic aggregate production planning in this lecture and then continue a detailed discussion in the next lecture. Now having seen forecasting models, let us now look at the aggregate planning or the production planning problem where we use the results of forecasting. Now, let me explain this problem using the spreadsheet. Now, let us assume that there is a single product. Right now, there is only one product that the company makes, and that we have made the forecast of that product, which is shown here. So, in this sheet, what is shown as demand is actually the forecast of the demand for the next 12 periods, which represent the 12 months. We also right now assume, by looking at this data, that this forecast is for a product which exhibits certain seasonality. So, there is a demand which is the forecast of the demand, which is shown here. Now, let us assume that there is a beginning inventory of 1000 units at the beginning of January that is available at the beginning for use. Now, we are also going to assume here that it actually takes about 10 hours to produce one unit, and that there are 65 people working, and therefore, we also assume that the organization works for 16 hours a day, and so on. So, all these assumptions finally give us that it is possible to have 104 units which are produced in a day using what is called a regular time production. Now, let us spend some time on this spreadsheet. Now, this column shows the 12 months of the year that we have, and right now let us look only at the beginning inventory of January, which talks about 1000 units. Now, demand or forecast of the demand is known here, and this adds up to 30,300. Now, we also have what is called RT days, which is the number of days available in each month for regular time production, and these are 22, 18, 22, 19 and so on. So, this data is also known. We also have what is called OT days, which means the number of days available for overtime in each month, which is given by 4, 4, 5, 4, 5 and so on. Now, if we have 22 days available in January, which is shown here, now we can produce 2288 units in January, a maximum of 2288 units, which comes from 22 multiplied by 104. This also is known and can be calculated once these numbers are known. Once the RT days column is known, RT capacity can be calculated. We can also calculate the OT capacity column, because in a maximum of 4 OT days available for overtime, 104 into 4, which is 416 units, can be produced using overtime. So, this column can also be calculated once the numbers in this column are known. Now, we can also calculate the total capacity in each month, which is the sum of the regular time capacity and the overtime capacity, as shown here also. The first term represents regular time capacity, second term represents the overtime capacity. So, this is also known. Now, we are going to ask ourselves this question: what is going to be the total production in each month, so that we try and meet the demand or forecast of the demand. So, now as a user, let us say that we start filling these values, which are the total production in each month. So, if we fill this number 2704, right now the total capacity that is available to the left is going to guide us in filling these values as total production. So, total production cannot exceed the total capacity in each month. So, if we fill a 2704 as the total production for the month of January. Now this 2704 has to be distributed to regular time production and overtime production. There is a regular time production cost of 100, there is a overtime production cost of 130. Since it is cheaper to produce in regular time, out of the 2704 that we have decided, 2288 will be produced using regular time and the balance will be produced using overtime. So the moment the user types 2704 here, it will automatically give 2288 to regular time, which is the maximum RT capacity, and the balance will go to overtime. So the user actually fills the production quantities for each of these 12 months. Now the moment the 2704 is typed by the user, now there is a beginning inventory of 1000 which is available here. There is a total production of 2704. So we get 3704 less 3000, which is the demand, gives us the final inventory of 704. So the ending inventory for January is calculated this way. Now what are the costs? There is a regular time production cost, there is an overtime production cost, there is an inventory carrying cost, there is a shortage cost. Now we have already seen that the regular time production cost is 100. So to produce 2288 units, the cost is going to be 2.288 lakhs. Overtime cost is 130. To produce 416 units, it is 416 into 130, which is 0.5408 lakhs. Ending inventory is 704 units. There is a 20 rupees for the inventory cost. So 704 into 20 would give us 0.1408. Since ending inventory is positive, there is no shortage, so shortage cost is 0, and the total cost is a sum of these 4 costs, 3 costs in this case because shortage is 0, it is 2.9696 lakhs. Now the ending inventory of January, which is 704, will become the beginning inventory of February, which is 704, and if we decide to produce 2288, which is the actual capacity, we have a negative ending inventory. We can calculate the RT cost, the OT cost. The inventory cost is 0 because there is negative ending inventory, and the shortage cost is 0.04 because 8 units are short, shortage cost is 500, 500 into 8 is 4000, which is 0.04 lakhs. So total cost for February is 2.4528. So like this, the user will type the values for the total production for the 12 months, and we can write this spreadsheet in a manner that the total cost is 33.1738 lakhs. So if the user chooses to produce 2704 in January, 2288 in February, and so on, the total cost is 33.17 lakhs. The question is, what should be the production quantities in these 12 months such that the total cost is minimized? Now this problem is called the aggregate planning problem, where given capacities and given the forecast of demands and given the various costs, in this particular spreadsheet we have used regular time cost, overtime cost, inventory cost, and shortage cost. What should be the production capacities such that the total cost is minimized? Now this problem is called the aggregate planning problem, and we will see more about this problem in the next lecture.